Welcome back to your fourth week of official at-home learning. This will be gloriously the last week that you're going to be taking active notes where it's mostly lecture-based. We're going to be learning about light this week, which just happens to be one of my favorite topics of the whole entire year. It's just fascinating to me, and at the heart of what science is wonder. So it's a good start, right? Besides that, next week we're going to be starting our final project of the year, which will take the last 2 weeks up there on really it might be a selection of two different things where you can either be building a solar oven or perhaps some kind of acoustic device, meaning something that can either capture and absorb sound or help to reflect it in a certain way to amplify it, kind of like an instrument. So that'll be next week, though. This week we have just 3 assignments that are video assignments and then 1 e-science. Also worth note is that this is going to be really the last week for grades. I'm going to be finalizing my grades this weekend. That's if you're listening to this now, it's Tuesday, most likely. So that'll be this Friday, Saturday, Sunday is when I'm going to be finalizing grades. So if possible this week, try and get your work done by 3:15 on Friday. Remind you, your grades can't really go down as a result of what you've done, but if you want them to go up, you have to do stellar work. So if you have a B, you have to be getting above a B if you want really anything to be improved on your grade for the third quarter. Okay, so I'm just going to take a second, like usual, for the very first video assignment of the week to just go through what you should be looking at as a student. I always start out with the weekly update. So you should read this carefully. Whatever your Google Classroom is, it'll sound something like this about the grading. Once again, it's this Friday, Saturday, Sunday is when I'm going to be wrapping it up, and I'm going to have that put in there for early next week. No ifs, ands, or buts. I'm not going to go back in time to change people's grades when you had all this time to do this work. And really, the way to improve your grade is just to get your work done this week, right? It's really brings up your grade a lot just to get your work done during these weeks. So there's no like, hey, yeah, I'm gonna whip my wand around and give you an A from a D this week when you haven't been getting any work done. Just get your work done. You'll improve your grade. This should be a no-brainer. The Google Meets this week will have 2 for each of the sets of classes. Just take a look at the schedule there. The first lesson for the week is going to be the nature of light. That's this lesson here. The second one will be on the interactions of light, and then the third one will be on the eye. Next week we'll talk about color a little bit more, and we'll be doing the project like I said. So if you have not completed your elective preference form, that's the form that kind of tells the school what you want to do next year for your elective courses, then you really need to go to the bottom of the weekly update and click on the course catalog, which tells you about the different types of courses you might be able to take next year. Some of them have different rules and stuff for applying for them, but it doesn't hurt to look. And then click on this link here, the Google form, to actually complete your choices. Until you've submitted that form, the school won't have any idea necessarily of what you want to do next year. So don't complain, hey, I can't believe that I got agricultural science, when you have the chance right now to actually give some input on that. And I'm not ragging on agricultural science, it's just the first one that comes up on the list, really. So that being said, if you have any questions about that, just ask me on email. But yeah. The other place you should be checking each week is Class Dojo. So in Class Dojo, if you're to come to the top here, Miss Bragg said something to 6th graders, not for us. The 7th grade schedules for this week, so you know what classes you have and when, are posted here. These are really important information. Please read it. I'm not going to take any more time than that. Happy Memorial Day to everybody. Parent surveys and student surveys. You can take your surveys. Basically, for your parents to take these surveys, they click through here. All the information's here. That's really helpful for the school. Part of why Baldy's #1 middle school in the city is because one small part of why we're #1 is because we have a lot of participation in surveys and things like that. That all adds into our total score as a school. So it's an easy thing to do. You know, your parents or guardians might win a $25 gift card. The puppy will be happy. And maybe the last announcement is just to Name my students that we're celebrating Ramadan. Uh, just happy Ramadan. I know it's over now. I hope you were able to enjoy your holiday, and welcome back to eating during the day. I'm sure it's nice too. But no, really happy holiday to you as well. Lots of stuff to celebrate this week. Also, two of your teachers' birthdays are this week. That's if you're in 701 through 703. Just one if you're in 704 through 706. I'm not going to say who. Just saying, it's there. So back to this. Here we go. Light. The nature of light. If you're in here right now, please open up your guided notes as well. That will be these notes here. You notice I have not made them quite as intricate this week. I realize it's a lot to take notes and to do the lesson itself, so just trying to break it down to the very, very bare minimum here, making sure that you're taking notes either here or in your own personal notebook or your own Google Doc. This isn't something you have to submit for the grade. That'll be the exit ticket, but it is something I'd like you to do nonetheless. Sometimes it doesn't match up perfectly, but you do your best here. Okay, so the nature of light. Waves, just a quick review here. You have wave types being broken down by what they need to go through. If it needs a medium, we call that mechanical if it needs something to go through. If it doesn't, the only type of waves that don't need something to go through are electromagnetic. So this is kind of like categorizing by it needs a medium or not. Also, not related to necessarily whether they need a medium or not. We can stupid bar on the bottom. Oh well. We can also categorize them by their shape that they take, which is based on what kind of disturbance makes them. Is it a back and forth disturbance in the same direction as the wave itself? That'll be a longitudinal wave. That's like sound. Is it something that's actively pushing matter up and down that causes the wave to go perpendicular to the direction of the matter vibrating? That would be a transverse wave. We've said many times already that light is a transverse electromagnetic wave, but now we're really going to get into like what the heck and why that is. We'll talk a little bit about the properties of it as well, amplitude, wavelength, frequency, and wave speed, and then we'll talk about the interactions, things that it can undergo, like things that can happen to it next lesson. For the third lesson, we'll talk about the eye, which involves all this stuff. Okay, so what is light? Here's the objective. Explain the relationship between visible light, the electromagnetic spectrum, and sight. Starting with light. Well, light is a form of energy emitted by the sun, but not just by the sun. If you can stop to think for a second, what else besides the sun emits light, emitting meaning that it gives off light. If you set a light bulb, boom, that's one easy example. You're probably looking at a screen that's producing light even right now. But you'd be surprised to think that most of the stuff that you see is not stuff that emits light, it's stuff that reflects it. Before we get into too much of that though, we should still take a little bit of time to think about what the heck it is. So, just for a second here, we're going to step back into 100 years ago. People were still trying to figure out what light was. Isaac Newton was very interested in what light was. He had proposed that it was a particle. He didn't know what kind of particle. He imagined it was very small, and he realized it was very, very fast. And he did a lot of experiments into light, but he didn't quite nail it. Fast forward a couple hundred years to about 150 years ago, I guess. This guy named Hooke, that was in, not like the pirate, but a guy in Britain. Maybe he was a pirate in his former days. It has an E on the end of it, Hooke. Tried to understand what light was, and it seems like a funny experiment, but it's called a double slit experiment. Basically, take a piece of paper, you put two small slits in it, and you take a good old electron beam gun, which isn't as dangerous as it sounds. It just shoots out an electron at a time, and he shot it through the double slit paper. Well, you call it paper. And you say, like, what would happen on the other side of that paper? What would you see? And what would that tell you about light? So take a second to think about that. Okay, so you had no exactly idea about what it would look like. It would look something like this, which is kind of weird to think about. you might have expected a million different things, but you probably didn't expect that, right? What this shows here is clearly an interference pattern, which means that the electrons and therefore light that go through these double slits, he did it with light really, would create a pattern that shows waves interfering. If you remember back to thinking about ripples in a pond, if you took two little rocks into a pond, those ripples would go out and kind of cross over each other and cause places of constructive interference and destructive interference. Well, when this guy shot these electrons through the double slit, he saw places of constructive interference, here, here, and here, and destructive interference, these places that have no pattern of the electron hitting it. Which is like, okay, I don't understand why it's such a big deal, but it is a big deal because it means that light acts as a wave. Waves interfere this way, particles do not. Particles just take their own hit, right? They're going to go this way, that way. It's like bullet holes in the screen, right? When you have these actual particles interacting with each other, it's kind of weird to think of it as a particle still. It's basically acting like a wave. So people thought for a long time then it was a wave, but a guy named Einstein did not totally buy that. By the way, this is a good video if you wanted to understand more about what that experiment was. Kind of complicated. Just for now, we'll say it's enough evidence to support a theory that light acts as a wave. But fast forward some more, you have a guy named Albert Einstein. You know, he had his theory of special relativity, of general relativity, E equals mc squared, all that good stuff. But the thing that won him a Nobel Prize wasn't any of that. Mathematicians, which was really what he was doing with that, were not granted Nobel Prizes. His Nobel Prize was awarded for explaining the photoelectric effect, which effectively classified light as also a particle, which was kind of mind-blowing for people. So at this point, people went from thinking it's a particle to now it's a wave. Now people are going back to saying it's a particle again. This is not an easy thing to explain. It's actually kind of weird, but I'll explain it anyway. So Einstein and people before him had realized that when you shoot photons, which are what we would call light, right, onto a metal plate, certain metal plates will do this differently, but just say it's a plate of aluminum, right? As those photons hit the aluminum, which is represented in that left picture there, they wouldn't come off. But you increase the frequency of the photons, not just how much of it, it doesn't matter how bright it is, just the frequency of it to a more energetic form of light, like blue light or violet light. All of a sudden, these electrons start shooting off of it. Like I said, I'm not going to explain how this works. It's really complicated. I could probably take a half an hour and not do it justice, but I will say that this proves that light is a particle. So it was confusing for people. You know, it's like, no, it's a wave or it's a particle. Einstein said it's both and deal with it. And people dealt with it and gave him a Nobel Prize, even if they didn't understand it probably, let's face it. So what is light? We're just going to call it a form of energy that travels as an electromagnetic wave and is a particle called a photon. So the photon is really talking about packets of energy that travel on these electromagnetic waves. So it acts like a light, like a particle, because it has the ability to impart momentum to something else, kind of like those pool balls or like a bouncy ball hitting somebody else. It's going to bounce them. That's the same way that light's working. That's basically the gist of Einstein's experiment here. So it's weird, right? It can travel through empty space or matter. It doesn't need to travel through something, but it can travel through stuff. It's kind of weird. This is another representation of what the graph of an electromagnetic wave looks like. It's really just these pulsations of electric fields and magnetic fields. The B is the magnetic and electric is E. So they go perpendicular to each other. You can't really tell where light is. It's not like light is anywhere on here. It's not like a duct that goes up and down like a wave shows you. It's actually just somewhere in there is the energy that pulses, and it travels in the X direction because of these two forces acting on it. Like I said, strange and awesome. We're going to dig into this more and get a lot easier right after this. So come back to the next video.